Hello everyone. I thought it would be kind of a good idea to just do some videos from now until the end of the semester, sort of showing you through some of these concepts, because from now until the end of the semester, you're going to be dealing with some the concepts are going to get more technically involved, and they're going to get, I would say, probably more difficult for some people. So I thought these videos would be a nice idea to sort of have a nice point for you guys to go back and review. Maybe you're reviewing for a test, maybe you're reviewing for the quizzes, maybe you just want to get reacquainted with the material, maybe you just want somebody else to explain it, I don't know. But I just thought these videos would be a good idea for those of you who wish to go back and review some examples and some of the stuff behind these problems. So equilibrium. So equilibrium is a very vast topic that you'll be talking about this semester, and the basics of equilibrium can be summed up by this generic equation here. A plus B going to C plus D. So these two things are happening simultaneously. A is producing C, A and B are producing C and D, and then once you make enough C and D, they start producing A and B. So they're just going back and forth until they reach equal rates. Equilibrium is the state at which A and B is produced at the same rate as C and D. So that's just sort of some of the basics behind equilibrium. And one of the big concepts with equilibrium and looking at reactions that happen at equilibrium is calculating the equilibrium constant. So I'll put that down here. So looking at the equilibrium constant, this is related to something you guys talked about before, the rate constant. So before break, you guys talked about little k, which is considered the rate constant. And you guys went through the process of calculating it. And that's all well and good. But now we're going to talk about the equilibrium constant, which is big K. So you'll always want to write the equilibrium constant as a capital K. And sometimes you'll see just a generic equilibrium constant written as K EQ. The EQ means equilibrium. But there's two common ways and to write the equilibrium constant, and these are the two ways you'll see it written throughout the rest of the semester. So one of them is Kc and the other is Kp. So Kc is going to be used when you're dealing with more aqueous solutions. Where you're dealing with things in molar concentrations. Kp is when you're dealing mostly with gases, because the P in Kp stands for pressure. And so you'll oftentimes in this course see gases in atmospheres. So atmospheres, ATM, is the unit we mostly use for gases. So when you see gases, think Kp and vice versa. When you see Kc, think concentration, because the C stands for concentration. So Kc is for more aqueous solutions where we have a molar concentration. Think acids and bases and things like that. And then Kp is used for gases that have a pressure attached to them. So gases measured at a certain pressure is when we're going to use Kp. Okay? So now let's break down, now that we've gotten a sense of equilibrium constant, let's go ahead and talk a little bit about equilibrium expressions. And this is where you're going to apply what it all means. So equilibrium expressions. So if we were going to revisit our previous reaction, so let's take A plus B at equilibrium with C and DD. So let's use this as our generic equilibrium reaction, and we can use this to develop a generic equilibrium expression. So your generic equilibrium expression is going to be K EQ is equal to the ratio of the products divided by the reactants. I'll say that one more time. The equilibrium constant is equal to the ratio of the products multiplied together divided by the reactants multiplied together. We're going to use these coefficients as our exponents, and I'll show that in a second. So on top, we're going to put our products over our reactants. Just like this. So this here, this thing that I've just circled, is our generic equilibrium expression. This is how your equilibrium expressions are going to look. You're going to have a K equal to products multiplied to each other divided by the reactants multiplied to each other. These exponents that I've just circled, like C, are going to come from the coefficient in front of each compound. So this C that I've just circled matches up with this C here, and so on and so forth. This D comes from that D, etc. Okay? So that is the basics behind this. Now we can look at a specific example, and hopefully when we apply it to the example, it'll all start to make sense. So let's take the following reaction. Let's take H2 as a gas plus Br2 as a gas, and it's going to be in equilibrium with 2 HBr as a gas. And the reason I'm including and being so specific about these states of matter is because, and I'm going to write this over here, and I'm going to strongly emphasize this, do not include solids or liquids. So do not include solids or liquids in your equilibrium expressions. I'll say that one more time. Do not include solids or liquids in your equilibrium expressions. They do not affect the rate of equilibrium, so they are not included in the equilibrium expression. Do not include them. Only include gases and aqueous compounds. So only gases or aqueous compounds. Do not do not include solids or liquids. Only gases and aqueous. Since all of these are gases, we will include all of them in this particular reaction. So let's say that, excuse me, let's say that hypothetically at equilibrium we have 1.61 atmospheres of H2. Let's say we have 2.01 atmospheres of Br2 gas, of bromine gas, and let's say we have 1.33 atmospheres of hydrobromic gas. So what these numbers mean is that, let's say we measured at equilibrium, and this is at equilibrium, hydrogen gas has 1.61 atmospheres of partial pressure, bromine gas has 2.01 atmospheres of partial pressure, and hydrobromic acid has 1.33 atmospheres of partial pressure. And let's say that the first part of this question is to write the equilibrium expression. Let's say that's sort of part A of this question, hypothetically. So write out the equilibrium expression for this reaction. So what we'll do is, since these are gases, we're going to use Kp, and we're going to say Kp is equal to, so we're going to have products over reactants. So our product in this case is HBr, so we're going to have that on top. and it's going to be raised to the second power because the coefficient in front of HBr is a 2. Over the reactants, so our first reactant is H2, and we're going to have that to the first power because there's a 1 in front of that H2. We just don't write it, but there's a 1 there. So it's to the first power times the other reactant, which is Br2, and it's also to the first power. Okay, and so this is going to be our generic equilibrium expression for this reaction. Kp is equal to HBr to the second power over H2 times Br2. And let's say that the second part of this question asks you to find Kp, given the numbers at the top. So given these numbers here, these 3 numbers, calculate the Kp for this reaction, the equilibrium constant. So all we're going to do is plug in our numbers into our expression, and we'll do the math and we'll get a number out. So we have HBr on top, and our amount for HBr is 1.33. We're going to square it over our amount for H2, which is 1.62, I think. Yeah, no, 1.61, sorry. So 1.61 to the first times our number for Br2, which is 2.01. So we'll just write 2.01 here. And it's also to the first. So if you want to go ahead and do that in your calculator real quick, as I will do, you should get out an answer. So if you want to pause the video really quick and do this in your calculator, feel free. So if you do this math in your calculator, you should end up with Kp equal to 0.55. So this is going to be your equilibrium constant for this reaction. So this is about all we'll cover in this video. And in the next video, we'll talk about doing some ice tables in the context of equilibrium. So next video will all be all about ice. And so in this video, we covered how to write an equilibrium expression, how to decipher an equilibrium constant, and how to solve for the equilibrium constant of a reaction where you're given all the numbers at equilibrium without ice. And you'll get your equilibrium constant at the end. Okay? All right.